CS40 VHF UHF fiber DAS. And there's myself, and there's JD. Before we get into the details, I just want to go over through a couple of items. We have our sales map right here. We have 3 regions. The Western region, the big chunk in the gray, that's manned by Leon Parks. Real new to Westel, though he's been around for about 17 years, more or less, in the BDA or fire industries. If you haven't talked to Leon since he's been with Westel, he has an email address and telephone number there. Please reach out. And speaking of that, you don't have to write it down. Sometime after the webinar is over, we will send out links to the video recording and a PDF. And so all this information will be available to you if you don't write it down right now. In the Southeast region, we have David Merkel. He's been with us for, I don't know, 6 months or so. Again, if you haven't reached out to him, there's his phone number and email address. And then we have Bill in the Northeast region. Bill's been around for a while. I'm sure if you're in that Northeast region, you know Bill. But just in case, there's his email and telephone number as well. And JD keeps our distribution running smoothly. And there's his contact information. Some other contacts, what you might want to know, are customer support is Donna. And Donna, you call that 800 number, dial 1, you'll get hold of her. And our technical support is Kevin. Kevin, dial that same number, but then hit 2 and 3, and you'll get hold of him. And then for IB Wave Designs, or sales engineering, is Zach. And he has a different number there that reaches him directly. And all 3 very good people to talk to about whatever you need to talk to them about. Most of our customers buy our products through distributors. And these are the distributors that we have. So again, just take a quick look at that if you're not familiar with it. But again, you'll have a copy of this later on, so you'll be able to look that up. So let's actually start why you tuned in here for. So we're going to talk about duplexing first. So when I go over the VHF model numbers and the UHF model numbers, if you don't understand exactly how duplexing works with UHF and VHF units, you're going to be a little bit lost. So before we go over those model numbers, we're going to do a little overview on duplexing, what it is, and how is it implemented in the Westel products. And then knowing that, the VHF and the UHF model numbers will make a lot of sense. We'll talk just a little bit about the mechanical specifications of the units and then the RF specifications of them. The battery backup unit, we'll talk briefly about that. How do we power this thing up as a secondary power supply? And just some real quick overview of how easy this thing is to commission through its graphical user interface. And then we'll finally talk about the new products. I mean, how do we turn these VHF and UHF BDAs into a fiber DAS master? Westel's been selling UHF and VHF BDAs for a long time, but they haven't been fiber optic compatible up until now. So what have we done, and how does that make that happen? So we'll go over a fiber DAS overview, and then we'll go through the details of how that happens. And then finally, some part numbers, and then we'll open it up for questions. And by opening up by questions, what I mean is you're going to type them in. Your microphones are going to be muted, so you won't be able to ask the questions, but you'll be able to type them in. And at the end of the webinar, JD will tell me what those questions are, and we will try to answer them as best as we can in real time. So let's talk about duplexers. So this is a very simple block diagram of how BDAs work. And as you can see, we have a duplexer on the donor port on a typical BDA, and we have a duplexer on a service port. I'm just going to concentrate on the one with the service port for right now. And for right now, it says duplexers allows one antenna to be shared for downlink and uplink. So we can see that here's one indoor antenna That is both the transmitter of downlink and the receiver of uplink. So one antenna that does downlink and uplink. And so how does a duplexer work? Here's what we could do. Let's just say that we just put in, let's say, a two-way combiner there instead of this duplexer. Would that work? In other words, would the downlink from the high-powered amplifier go into this port of the combiner and then go to the antenna? And then when there's an uplink signal from the antenna into the now a splitter, it would come out both ways, but the signal going into the high-powered amplifier wouldn't do anything, but the signal coming here would go into the LNA. Why can't we just not use a duplexer and put a two-way combiner there? And here's the reason, is these combiners don't have what's called a lot of isolation between the two ports. The better ones, like this Wilkinson one, has about 20, maybe 25 dB of isolation, meaning that whatever signal power comes into here, almost all of it's going to come out of this combined port, but about 20, 25 dB less will also come out of this port. And in a lot of situations, that's, 20 dB is 100 times less. So that's a lot less power. But in this case, it would be a disaster. This high-powered amplifier for some of our UHF units are 5 watts or 37 dBm. And if 37 dBm came out of here and went into this port, and 20 dB less came out of this port, that would be 17 dBm coming out of this port and going into a low noise amplifier. And there's a couple things we can say about low noise amplifier. One of them is they're really, really great at amplifying weak signals and not adding a lot of noise. But what we can also say is they don't like strong signals. They can get overloaded and physically damaged by too much of a strong signal. And plus 17, that's way, way too much for an LNA. So this two-way splitter just isn't going to work because there's not enough isolation between the downlink power and the uplink power into the LNA. And basically what would happen is that LNA is just going to say, ouch, and it's downhill from there. So what we're going to do is we're going to place that two-way splitter with the duplexer. And what exactly is in this duplexer that prevents that problem from happening is we use filters. We use passband filters. Passband filters will allow a certain group of frequencies through while blocking anything lower and higher. And so the downlink frequencies are going to go through a filter that only allows downlink frequencies through. And then we're also going to have a second filter is for uplink. And this filter will only allow uplink frequencies through. So just picture a downlink frequency coming out as high-powered amplifier. Can it go through this filter? Yeah, it can go through that filter. And then it gets to this junction right here and it says, okay, my signal can either go to the antenna or it can try to go to the LNA, but it can't go to the LNA because this uplink filter doesn't allow those frequencies through. There's a lot of impedance and it just won't go, so all the power will go to that antenna. And then when an uplink signal travels into the antenna and gets to this junction, it's not going to be allowed to try to go into the output of the high-powered amplifier because this filter is going to block uplink frequencies. But that uplink frequency will go right through this passband filter and into the LNA. So that's basically what a duplexer is. Duplexers just have filters that filter the downlink and the uplink. And the idea here is that whatever rejection this filter has for frequencies outside of downlink attenuates the signal enough so that if some comes through, which it will at some level, but it's way, way less than what this LNA will have a problem with. The LNA won't have any problem seeing a very low level after it goes through this uplink filter. So that's what a duplexer does. And we do the same thing over here on the donor side, except now the problem is the uplink high-powered amplifier could overdrive the downlink of the LNA. But it's the same process. We just filter them out so that that's not a problem over on that side. Now, if we look at a 700, 800 BDA, these guards, what we call guard bands, are easy peasy to do. We have downlink frequencies separated from the uplink frequencies by 30 megahertz on the 700 band and by 45 megahertz on the 800 band. And if we were to look at the 700 band, we would have a filter for the downlink frequencies, only let those through, another filter for the uplink. And as far as these filters, they're really easy to design because there's a lot of distance, a lot of frequencies between the two. So 30 megahertz, any good RF engineer can come up with filters to make this work. And what else makes it nice is it's the same filters nationwide. I don't care if you're on the left coast or the right coast or up near Canada or down near Mexico. These 700 frequencies and the 800 frequencies, for that matter, are the same everywhere. And so Westel can crank out these duplexers, and it doesn't matter where they go because it's the same everywhere in the United States. Now, let's take a little bit of look at a UHF band. This is not the full UHF band, but just a portion of it. And you can see that there are no built-in guard bands. Here's the downlink for UHF 450 to 455. And right next to it, with absolutely no guard band, are the uplink corresponding frequencies. And then we have another section of the spectrum for downlink again and uplink again. And again, no guard band between any of these things. So this makes it a little bit challenging. So let's look at a couple of different scenarios. Here's a jurisdiction that uses 3 downlink frequencies, and those are represented by those blue arrows. The corresponding uplink frequencies would be 5 megahertz higher, or these red frequencies right there. And what we have to do at Westel is we have to tune our own duplexers to make sure that those downlink frequencies don't mix up the uplink frequencies on either side. So we're going to take some filters and we're going to custom tune them so that they allow those 3 downlink frequencies to be in the passband and those 3 uplink frequencies to be in the other filter's passband. And we make sure that they stay out of each other. There's no overlap. And this, we can only do that if you tell us the downlink and uplink frequencies. This is going to be true with our UHF and our VHF products, is until you tell us what the downlink frequencies are and the uplink frequencies, we cannot tune these filters, because unlike 700 and 800, where they're the same everywhere, these filters have to be tuned based on the frequencies that your jurisdiction uses. And they can be all over the map. And until we know specifically what they are, we don't know how to tune those filters. So this is an example of something we call a single window duplexer. All right. Now, let's say this jurisdiction not only has these groups of downlink and uplink frequencies, but they have a second set. Well, here's 4 downlink frequencies up there in the 460 range, which have a corresponding 4 frequencies in the uplink range. These filters that we've already tuned, they're not going to do any good with this second set of frequencies. So we're going to put in a second set of filters so that they don't interfere with one another. And this would be an example of a dual window duplexer. Now let's look at another case. This jurisdiction has 3 downlink frequencies, just like the other one did, but they are spaced kind of far apart from one another. They're still in the 450 to 455 range, but they are spread all across that 5 megahertz. The UHF corresponding frequencies are going to be those 5 megahertz above. And what happens is we have this area right here where the highest downlink frequency and the lowest uplink frequency are fairly close together. Can we have a filter that keeps this downlink frequency out of this uplink frequency on the service side and this uplink frequency out of this downlink LNA on the donor side. And often, well, I wouldn't say often, but sometimes when we put our filters in there, those frequencies are just too close together and the filters would overlap. And we can't provide enough isolation between the two. And we would definitely overload that LNA with the filters that overlap too much. And when we do that, do we just give up? And the answer is no, we don't give up. We provide another solution, which is called a 4-port solution. And by the way, how close do these filters or frequencies need to be? It's approximately around 1.5 megahertz. If these two frequencies are 1.5 megahertz apart from one another, there's a good chance you have to go to a 4-port solution. There's a little wiggle room there, but that's overall the rule of thumb. If those are closer than 1.5 megahertz, you might have to go to a 4-port solution. So what a 4-port solution looks like is here's our UHF BDA. And what we're going to need is we're going to have 2 donor antennas, one for uplink, one for downlink, and we're going to have 2 sets of service antennas. Again, one for downlink and one for uplink. And how does this work is we need physical separation between the 2 antennas. So let's look over here on the service side. This downlink antenna, we could say, can have as much as 5 watts coming out, going into this antenna. And it's going to transmit that signal, and some of it's going to be picked up by this uplink antenna, and then it's going to go over here to the LNA of the BDA. And we got to make sure that that signal level is low enough so it doesn't overdrive that LNA. So what we're going to rely on is free space path loss. We got to make sure that these antennas are far enough apart that when this thing transmits maybe up to full power, by the time it travels through the air and loses power and then travels through a coax cable, but it gets to the BDA at a low enough level not to overload the LNA. And it varies by different things, but prepared to be about 60, 70 feet separation between those downlink and uplink frequencies to make sure that that happens. The testing of this BDA is a little more complex than a normal one. Every BDA, you need to do isolation testing between the donor and the service port. When you have a 4-port design, you also need to do isolation between the downlink and the uplink antennas, both on the service side and also on the downlink side. So there's actually like 3 isolation tests you need to do. All right, so now it's time to take a look at the model numbers. Now with everything explained, I think everything will understand. So we have high-powered UHF and VHF units, and we have mid-powered UHF and VHF units. The first thing I want to go over is the UHF high-powered unit. We can take a look at this model number, and the key here is the second set of numbers and letters, U37. So the U is going to be a UHF unit, and the 37 is the dBm of downlink output power. So this is a 5-watt UHF unit, and it's going to be the 4-port, or sometimes it's called simplex design. So no duplexer, just 4-port simplex. We also have a high-powered single window and a high-powered dual window unit. Now we also have mid-powered units. Here we have a 4-port simplex version. This is the unit we've been selling for years, this model number right here. And what this webinar is this red model number here. Pretty much the same model number, but instead of an A0 at the end, it's an HE for head end. This has all the connections needed for the fiber DAS master. So we're going to sell both units. This one, the one in black, will always be a BDA and nothing more. Standalone BDA. The one in red, this can be a standalone BDA as well, but it can also be expanded to be a fiber DAS master. So if you have a project that is maybe one building today, but in the future they're going to have a second building or a third building, it might be wise to put in the FiberDAS master version in the primary building, and then as the project expands, you just add remotes instead of additional BDAs. So that requires a little forethought if you know that this project is going to expand. And here's what you're going to find out. These FiberDAS masters here, we're going to offer them in the mid-powered units only, not the high-powered units. So the high-powered units will not be FiberDAS master. This mid-power UHF unit is 34 dBm or 2.5 watts. Now we also have a single window duplex version, both standalone and FiberDAS master. And we have a dual window duplex version, again, standalone and FiberDAS version. As far as VHF is concerned, you can tell it's VHF by this model number with the V and 30 dBm. So that's 1 watt of downlink output power, which is our high-powered version. And it covers the entire VHF band from 150 to 174, and it's simplex. Now we have 2 duplex versions, just a single duplexer, single window. And the difference is that this one, high-powered, only covers half of the VHF range, 150 to 162. And this one covers the upper half of the VHF range, 162 to 174. So definitely, even in the duplex versions, this is another reason we need to know those channels because it's 2 different model numbers depending on where those channels lie. But just like the UHF, we don't have any FiberDAS masters with the high powered, but we do for the mid power. So the mid power, the V is VHF 27, that's half a watt. So our mid-powered VHF units are half watt of downlink output power. And here the simplex version, just like high-powered, covers the entire range. And here is our model number for the FiberDAS master. And then we have a duplex version. And unlike our high-powered versions, the mid-powered duplex does cover the entire range, 150 to 174. So here we have 2 new model numbers for VHF that can do FiberDAS master. Mechanical specifications. These cabinets are larger than 700, 800, just longer wavelengths, so bigger components. And I'm not going to go read everything here, but key here is the height, width, and dimensions is 29 by 20 by 13 by 8. And the weight has a very wide range, and this depends. The 79 pounds, that's the simplex version without a duplexer. And the 135 pounds, that's the duplexer. So that's the weight of the duplexer, but the difference between those two. And then everything else is pretty standard. Do want to mention that we use N female connectors. If you're familiar with some of our 700, 800 products, they come with 4.3-10. But the VHF and UHF units are N female. And everything else is pretty standard. And for UHF, again, a little bit bigger cabinet, and its weight is 79 to almost 160 pounds. So 79 pounds would be the simplex version. The 160 pounds is the 2 duplexers or the dual window. And then halfway in between would be the single window. And everything else is pretty standard stuff. VHF, like we mentioned, overall is 150 to 174, but we saw that the high-powered versions, that varies a little bit, but for the mid-powered versions, that's what it is. It's 27 dBm or a half watt for both uplink and downlink. And that power can be adjusted 30 dB down from that. So we can go from -3 dBm up to 27 dBm in 1 dB steps for both uplink and downlink, completely independent of one another. And as far as gain, we have a maximum of 85 dB of gain, and once again, a 30 dB range. So we can go from 55 to 85 dB of uplink and downlink gain in 1 dB just steps, and also completely independent from one another. If you put it in the Class A mode, we have 16 filters with 12.5, 25, 50, and 75 kilohertz passbands. And if you put it in the Class B mode, we have 4 filters that can be 700 kilohertz or 0.7 megahertz, 2, 3.5, 5, and then the simplex version would be the entire 24 megahertz. And we do donor and service port VISWAR measurements. The mid-power UHF unit, overall, 450 to 512 is the UHF bands that we cover. And again, mid-power is going to be 2.5 watts or 34 dBm of power. Uplink is a half watt or 27 dBm. And just like the VHF units, we have a 30 dB range and 1 dB steps for both maximum output power and gain. And the filters are the same. The only difference is with the Class B filter, it's a total of 62 megahertz if you wanted to amplify the entire 450 to 512. As far as battery backup units, it's the CS19 BBC, the battery backup cabinet 003. It is used for both VHF and UHF. It's also used for our 700-800 CS40 BDA. And this thing is pretty simple battery backup. It has 2 batteries, a circuit breaker, and some wires. It's a very, very simple design, but it works great because it's so simple. You're going to take 2 batteries, you're going to wire them in series, call it 24, call it 28 volts, somewhere in between. That's what you're going to get. And we have 3 battery options. We have a 4-hour battery backup option for those generally be used if there's a generator being used as the main secondary power source. Then we just need a little bit of batteries to make sure there's no glitches when AC goes out and the generator kicks in. And then we have the standard 12 and 24-hour batteries. 12-hour batteries, 100 amp hours. 24 is 160 amp hours. And of course, with all 3 of these, we're going to have 2 batteries each wired in series. The battery backup cabin, if you open it up, this is what it looks like. We have conduit ports on the top and on the sides. So when you're mounting this thing, usually it's below the BDA or off to the right because of where the conduit ports are. And one of these ports is a 1/2-inch liquid tight fitting. The fittings do come with the unit, but you do have to install them. And we also have a 3/4 inch one. There's a yellow interconnect wire that connects the 2 batteries in series. And then pre-attached to the circuit breaker is 72 inches of red and black wire to get the 24 volts from the BBC over to the BDA. So when you mount these things, just make sure that 72 inches of wire will reach. And then inside, we have 2 batteries. Here's the yellow interconnecting cable. And also pre-installed on the circuit breaker is another pair of red and black wires that connect to the batteries. And these are the 72 inches that go to the BDA. There is no battery charger in this battery backup unit. That is in the CS40 BDA itself. Quick look at the graphical user interface. It uses the same user interface as our CS40 700-800 and our CS45 700-800. So very, very simple. When you log in through Cat5 cable, RJ45 to RJ45, you just open up an internet browser, type in 192.168.1.150, and bam, you're in. No special software needed. And all the main menu is here. We got alarms, RF configuration, testing the alarms, and backup and restore. And you can see it. Just overall, pretty standard stuff. It's very easy to use. Here's what the alarms would look like if you clicked on the alarms. If it's the alarm is in green, we're good to go. If the alarm is in yellow, it means something's not quite right, but it's probably not service affecting, like a door open. But if it's red, that's a problem. Donor antenna disconnect, yeah, that would be a problem. So that's in red. And then if you wanted to mask an alarm, it just shows up in white with a strike through on the lettering. And so pretty easy to tell at a glance what alarms you have and if there's a problem or not. And when it comes to RF configuration, we have, like mentioned, there's 16 Class A filters and there's 4 Class B filters. And all you need to do is put in the center frequency and it calculates the uplink frequency automatically. That happens all the time in 700, 800, and a good bit of time in the UHF region. But with VHF, VHF is kind of like the wild, wild west where there's no set offset between downlink and uplink. It's not 30 megahertz or 45 or 5 or 3. It's all over the place. And in that case, we have this little lock right here. You can just click on here, which undoes the lock, and then you can custom put in your downlink and uplink frequencies, and they're not linked together. So this links them together. You click on it, they become unlinked, and you can put in whatever VHF uplink and downlink frequencies you have. All right, so now it's time to talk about the fiber DAS. Let's just do a quick overview as why would you want a fiber DAS? And that's available now for the CS40, UHF, and VHF mid-power BDAs that we went over earlier. And just so you know, this same configuration is also going to be available for our new 2.5 CS45, 700, 800. So yeah, all 3 of these frequency bands will use the same fiber DAS system. The CS45 is going to be available soon, not quite ready, still going through testing and approvals for UL and FCC and all that, but it's almost there. So why would you want a fiber DAS system instead of a standalone BDA? 2 case scenarios. One of them is a large building, and that downlink output power, to save even 5 watts, just isn't enough to cover all the square footage. So you could add more BDAs, but a better solution would be add just one fiber DAS system. And the other reason that people tend to use fiber DAS is a campus setting with multiple buildings all needing coverage. You could put a BDA into each one of them, but that's really not a good idea. A single fiber DAS solution would be better. So why is a single fiber DAS solution better than multiple BDAs? Is when you get BDAs close to one another and the donor antennas kind of start interacting and you can get oscillations, timing issues, uplink noise. You can completely commission one of those BDAs and say it's working great. And then you go to the second building and you bring that BDA up, and next thing you know, you broke the BDA in building number 1. It can be a nightmare getting these things installed and commissioned correctly. So avoid all that and use a fiber DAS system. So here's part of the, these are the 2 main components of the new fiber DAS system. We have the HE unit, stands for head end, and we have the remote end unit, RE. And what the head end unit does is it will get some information from the master, convert it into light, and send it to the RE unit. And the RE unit will take that light, convert it back to RF, and send it to the remote unit. And for uplink, it's just the opposite way around. And both of these units do come with alarm annunciators on the front panel. This alarm annunciator for the HE will show the alarms for the master unit. And this one over here will show the alarms for the remote unit. You're going to connect that HE and the RE together with a fiber optic cable. The specifications for that fiber optic cable is single mode. And then SC APC is the connector. SC describes the physical connector here. So this green connector right here, that's what an SC connector looks like. And then APC is angled physical connector, which means the glass actually has like an 8-degree angle on it. And that's usually designated by green. So this project overall should have green connectors that look like this with a yellow jacketed fiber in between, which is generally single mode. It's not like there's any laws that say these need to be green and this needs to be yellow, but overall, that's what most manufacturers have agreed upon. Now, this angle, the A of the APC, is very important. This is an analog system, and analog systems don't like reflections. And so it's very important that this angle is everywhere, including a patch panel. If you have a patch panel, it also must be APC. We don't want any, we'll say, flat ends, UPC or PC. They have a lot more reflection than APC, so we got to make sure it's everywhere. And as far as the specs, we put a light source into one end of this cable, and coming out the other end, it better not have any more than 5 dB of optical loss. So that's the maximum amount of loss from one end to the other, including any patch panels that might be in between. And as far as those reflections are concerned, whatever power goes in, when it gets reflected back, the reflection better be at least 6 dB below the power that went in. And that you have to measure with an OTDR, an optical time domain reflectometer. So let's see how this all looks. So here is either a VHF or a UHF BDA, one of the mid-powered units, connected to the battery backup cabinet. The red and the black wires are the 24 volts. And we're going to send 3 signals overall from the BDA to the HE. And what are these 3 signals? The blue line represents a Cat5, Cat6 cable. This is where all the data goes back and forth so that the system is smart. The 2 grayish looking connectors, these are SMA jumper cables. So SMA connectors on both ends. And that's to transfer the RF from the master to the HE. So one cable's for downlink, one cable's for uplink. And then the HE unit does not have any power supply at all. So the BDA master is going to supply the 24 volts to get it powered up. And I see I have a typo here that says 12 volts. This should really say 24 volts. 12 volts is for the 700, 800 unit, but this one uses 24. So this should be 24 volts of DC here. And that's going to connect up to the HE unit. The HE unit is going to take that downlink and uplink information, convert it to light, and there's going to be up to 4 fiber optic cables leaving the HE unit. These are the single mode SC-APC connectors we talked about. And those fiber optic cables, they're not going to go to the remote. They're going to go to the RE units. And that's where the RE, as far as the downlink is concerned, is going to convert that fiber optic and back into RF. And then it's going to feed those exact same 3 signals, Cat5 data, SMA, uplink and downlink, and plus or minus 24 volts, or just plus 24 volts, and send that to the remotes. So one HE can handle up to 4 remotes and 1 RE for every remote. And so the system you see here, you can have up to 4 remotes. Is 4 remotes not enough? Well, we can fix that. It turns out the HEs are daisy chained together to expand the system. So this is a simplified diagram of what I had before. And now we can daisy chain a second a second HE, a third HE, and a fourth HE. And each of those HEs can handle 4 remotes. So overall, a fully expanded system can have up to 16 remotes. Now, inside the HE, there's connections to daisy chain the plus and minus 24 volts to one another. And there's 2 RJ45 ports to daisy chain the Cat5 cable between the 2. Now, we still need to get this, the uplink and the downlink to each of these other HEs, and this is what we're going to do externally. So we're going to have a splitter that's external to the system, and that splitter is going to feed the SMA cables to each of these HEs. So for a fully expanded system, we would want a 4-way splitter, and one of the outputs of that 4-way splitter would go to HE number 1, then HE2, HE3, and HE number 4. So up to 16 remotes. Here's the ordering guide. So these part numbers over here we went over already. These are the master units that we described. And up here is the model number for the HE unit. Now over here on the right, here's the model number for the RE unit. And here are the model numbers for the remotes. The remotes have the same overall model number as the masters, except the master ends with HE for head end, and the remote ends with AR for a Class A remote. And these are paired together. If you, let's say, for example, have a UHF single window duplexed unit for the master, you're going to want that exact same model number for the remotes, so you want to match them up. And that is the end of the presentation that I have. JD, do we have any questions?
What is the propagation delay at 50 for the UHF?
All right, propagation delay. Yeah, 50 kilohertz. Bob, you're right on. 25 microseconds. And here's all the other ones, just while we're there. Anything else?
Yeah, we have a couple, Tom. So are the remotes UL channelized?
Okay. Yes, so this, the A does stand for Class A. And yeah, so all the uplink filtering is done in the remotes.
Can they manually adjust gains on each remotes?
No, the gains are set. We can adjust the output power for downlink, but the gains are set for the remotes. We can set the gain over on the master side, but the remotes, the gains are fixed.
If there is an application where you're using client fiber that is worse than 5 dBO, do you have a solution that can work at, say, 10 dBO like your competitors?
This solution is 5 dBO. Wow, that's 10 dB of optical loss is a lot. Either it's very, very, very far, or lots of patch panels, or I don't know what's going on with that. But 5 dB of optical loss, just straight, home run from one end to the other, that'll usually get you over 5 miles. But no, 5 dBO is what it is. If you have any questions afterwards, feel free to reach out. We're always here.